begin a discussion of factoring polynomials. This is a fairly large topic in an introductory algebra course, and it's used continuously on through the progressive math sequence. And what I have done is I've decided to put together a small flow chart, and we're going to, as we go from one video clip to another, work our way through this flow chart. When you factor polynomials, one of the first things that you should always do is you should take the greatest common factor out first. It's got to be your first step. In my flow chart, I've called that the GCF. So again, take your polynomial, get the greatest common factor out of it first. Once you've done that, I'm going to ask you to count the number of terms that are in the polynomial. My focus is going to be in this set of videos to take a look at the scenario where we have 2 terms in a polynomial, 3 terms, and 4 terms. We're not going to go in that order. We're going to start here looking at the greatest common factors and getting those out first. Then we're going to go to this topic. We're going to take a look at polynomials in 4 terms and factor those by grouping. Then we're going to look at polynomials in 3 terms, where the first term, the x squared term, has a coefficient of 1. And then we're going to work into some more difficult problems where the coefficient in front of the x squared term is not a 1. And then finally, we're going to work our way back, if you will, towards a polynomial in 2 variables. For the purpose of introductory algebra, we'll look at what's called the difference of squares. In intermediate algebra course, we will look at what's called the sum and difference of cubes. Let's go ahead and look at this greatest common factor. I'm going to just share several problems with you, and we'll work through them. First of all, I might just give you a couple of terms. For example, 2x squared and 6x, and I might ask you what the greatest common factor is of both of those monomials. The way you would think through this is that you think of 2x squared as 2 times x times x, and you would think of the number 6 as 2 times 3, and then of course we have that factor of x. And you look in these 2 groups and you see if they share anything in common with one another. Well, they both appear to have a 2 in them, so that's a common factor. And they both appear to have an x, but no more than that. This one does not have 2 x's. This one does. My greatest common factor to both of these is just a single factor of x. That is called my greatest common factor of these 2 terms. Now let's use that. Matter of fact, let's go ahead and just make that, remember 2x is our greatest common factor. Let's make this into a polynomial. Let's just put a plus sign in between. What I'd like to do in that first step in factoring, where I take the greatest common factor out, is I'd like to pull the 2x out in front of a set of grouping symbols or a set of parentheses, and then I have to ask myself, what would I need to put right here if I were to multiply 2x by that and get this 2x squared? And I would need an x right here, because 2x times x is 2x squared. And next, I would ask myself, what do I need to put right here if I want to get 6x when I multiply 2x by that? And I need a positive 3 here, because 2x times 3 is that 6x. This is the factored form of this expression, and it is the first step in factoring a polynomial, to take the greatest common factor out. Let's look at another one. So let's look at x to the 3rd plus 5x squared. In this problem, there is not a numerical coefficient that they share in common, but they do both have the variable x. This one has an x times itself 3 times, and this one has an x times itself 2 times. The greatest common factor is that variable x to the 2nd power. I cannot get out of this one x cubed. The most I can get out of it is x squared. So that's the greatest common factor. I'm going to pull that out. Now I'm going to need right here an x to the 1st power, because x to the 2nd times x to the 1st gives me x to the 3rd. We typically don't write that 1 there as an exponent. And right here, I'm just going to need a 5, because x squared times 5 gives me that 5x squared. You should always check, just kind of take a quick look and say, does x squared times x give me x cubed? And does x squared times 5 give me 5x squared? Let's do another. In this problem, they share a numerical factor. that is common to both of them. That's the number 5. A 5 can be pulled out of each one of those successfully. And in terms of the variable, we can pull out x to the 3rd power. So the greatest common factor in this one is 5x to the 3rd power. So right here, I will need an x to the 2nd so that when I multiply the 5x cubed, the greatest common factor, times this x squared, I would get 5x to the 5th. Remember, you're adding your exponents when you multiply. Right here, I'm just going to need a 2 because 5 times 2 gives me the 10, and I already had the x cubed there to complete this polynomial. Again, say it to yourself again, multiply it out and check it and see that it works. Let's do another, maybe just one more. Okay, I've created a problem where the numerical coefficients are quite large. One of the ways to find the greatest common factor is to write them as the product of their primes. That's an option. So this would be 2 times 2 times 2 times 2. And you do that with the 32, and you do that with the 48. Well, it happens that the common factors that these all share are those 4 2's, or a factor of 16. 16 will divide into 48 3 times. 16 will divide into 32 twice, and 16 will divide into 16 one time. So I'm going to factor out a 16, and next I have to decide how many PQs to take out of here. And it's got to be the least number in terms of their exponent, size of their exponent, the least number of factors in the P's and the Q's that occur in any one of these. This has got the smallest number of P's, it's P to the 1st power, and this one Q to the 2nd power. I cannot bleed any more out of that term than a PQ squared. So that's the most that I can take out of this whole expression. So right here, I have to decide what I would need to fill in so that when I multiply it by 16pq squared, I get 16p to the 6th, q to the 4th. Well, when I take this exponent of 1 and I add 5 to that, I get p to the 6th. And this q to the 2nd, I need p to the 2nd because when I add those, I get 4. I already had a 16 here. If you want to or need to write a 1, you're welcome to do that because 16 times 1 is that 16. My next term, I need a 2 because 16 times 2 is going to give me that 32. I need p to the, let's see, I've got a 1 here, I need it to get up to a 5, so I've got to put a 4 here so that when I add 1 and 4, I get that 5. I've got a q squared, so I need a q to the 1st here to get to q to the 3rd. Again, if you need to write that, go ahead. It's not very common that we would do that. And then finally, right here, I would need 16 times a minus 3, and then I'm all set for the variables. I've got the pq squared out here, and I'm done factoring this problem. I actually thought of just one more. Let's do a fraction problem. And so it looks like this. Let's take a fraction out of 5/9 x to the 6th, 2/9 x to the 5th, 4/9 x to the 3rd, and 1/9 x to the 2nd. As the variables go, I'm going to be able to get x to the 2nd power out of this expression. They happen to have the same denominator. If they did not, I would force them to have that. I would make that occur. And then the most I can get out of all of these, because this 4, this 2, and this 5 do not share any common factors out of all of them, and that 1 for that matter is the 1/9. So I can factor 1/9 out of every one of these, and I can get x squared out of them as well. To take this and multiply it by something to get 5/9, I better multiply it by 5, because 1/9 times 5 is 5/9. This x to the 2nd needs an x to the 4th, so that when I add their exponents, I get a 6. The next term, I better put in here a 2, because 1/9 times 2 is 2/9, and I've got this x squared, so I'm going to need an x to the 3rd to get up to x to the 5th. Next, in a similar pattern, I'll need a 4 here, because 1/9 times that minus 4 is that minus 4/9. I've got x squared, so I better put an x to the first here to get that up to x cubed. And finally, I do need to put a term here of a 1, because I got to show that 1/9 x squared times that minus 1 gives me that last term.